Great. So I'd like to thank the organizers for inviting me to speak here. I will talk about actually a sort of a coarse version of a well-known theorem. So let's say that in a certain way, one can say that the starting point for what I'm going to explain is the theorem of Bellman on rank rigidity. So let's consider this version actually. There are by now generalization even in the setting of Riemannian manifolds. So whenever one has a compact manifold of negative curvature, there is a dichotomy. So either that manifold is in fact a product of symmetric spaces, so implied of rank at least 2, so either a product of at least 2 or one of the factors of rank 2, or if not, there is one geodesic of rank 1 in the universal cover to begin with. What does that mean? That means simply that when we look at the space of Jacobi fields, of parallel Jacobi fields along that geodesic, that one is of dimension 1. And if we focus on such a geodesic of rank 1, this one has the following property, a sort of coarse property. It's so-called Morse, in the sense that whenever we consider 2 points along that geodesic and we join them by a quasi-geodesic, that quasi-geodesic must stay within a tubular neighborhood of the initial geodesic. So this is what we have, and I would also like to draw. So essentially that means that if we want to join 2 points by a path, and we want this path to travel efficiently, meaning that with time it will go away from the one endpoint proportionally to the time, and it will come close to the other also proportionally, so that's a quasi-geodesic, then this will have to stay within the tubular neighborhood of this geodesic, and the ray obviously depends on the quasi-constants. So other things that one can say in this setting, focusing on the fundamental group of this manifold, is that, first of all, actually, the group itself contains a so-called Morse element. So if we look at that element, and if we look at the cyclic group generated by it, its orbit, actually any of its orbit, is Morse, exactly in the same case, in the same sense, except of course here we're going to have a copy of Z, essentially. And it's Morse both in the universal cover and in the Cayley-graph of any Cayley-graph of G. And the other immediate property is that the fundamental group contains free non-abelian subgroups. So this is sort of the starting point, and now we would like to see how far we can generalize this. So to begin with, we'd like to work in a sort of a very general setting of non-positive curvature. So it's going to be a sort of weak form, and it will be essentially metric spaces that are endowed with Combings or bicombings. So I'll define this later. For the moment, I'm just sort of giving an overview of what we're going to talk about. And within this sort of setting of weak non-positive curvature, I'm going to look at how you can detect the presence of negative curvature, and using essentially two tools. First of all, Morse quasi-geodesics in the previous sense. So basically, I'm defining things randomly, and I don't know if everybody knows, everything. So please, if you want anything defined, absolutely anything, please ask, and I will do it. And so otherwise, let's assume that, so quasi-geodesics is something that you're familiar with. So these are, in a sense, hyperbolic directions in a space. And another way of investigating the presence of negative curvature is by means of the so-called divergence. Now, this one is a quasi-isometric invariant. Essentially, it was introduced by Gersten to measure how the rays diverge, so how they spread out. And it was at the time when people were still studying the geometrization conjecture, myself. But in any way, it was a way of looking at three-dimensional manifolds at the time. It's also a good way of investigating the topology of the boundaries and of asymptotic cones of certain metric spaces. And so now I think I'll start defining each of these items. First of all, what kind of combings and bicombings am I going to look at? So first of all, I should mention that a little bit of history. So as far as I could trace it, the first person who introduced this notion of sort of distinguished classes of paths joining pairs of points was Bussmann, but he did not use this terminology, the one of combing and bicombing. That one was introduced by Thurston, and he used it not for a distinguished class of geodesics, but for actually a distinguished class of paths. So we just take points and we join them by certain paths, and then we introduce some condition on those paths that is supposed to say that we have some version of non-positive curvature. Now, I'm not going to overview this. There are sort of all sorts of combings and bicombings. I will just say what are the assumptions that I'm going to use. I will consider always quasi-geodesic combings and bicombings. So essentially that means for every pair of points, we assign a quasi-geodesic. Please note that it sort of comes intrinsically with some orientation, and that is a source of problems, but I'm not going to, the problems have been solved, but they are there. But we had to cope with them. And then, so bounded simply means that whenever I fix a point, so let's say I fix the origin, and I'm looking at various quasi-geodesics joining 2 points. So either we write the condition like that, or we just say that if we have 2 points within distance, let's say at most 1, then the corresponding quasi-geodesics fellow travel at distance at most k. So this is a combing, and for a bicombing, we're asking for the same thing, but this time we allow for both endpoints to move. And then we have that kind of control. So they fellow travel in a controlled way if both endpoints are at finite distance. And here is sort of an extra assumption that we had to add, because we don't know how to do without it, quasi-consistency. So the quasi-consistency means that if I take one of these lines, and I pick 2 points in it, and for these 2 points I consider also the corresponding line, we want that this new line would be, so it's Z1 and Z2 in that notation, would be at uniformly bounded distance from the piece of the larger path, special path. So this is going to be, for me, the setting of non-positive curvature. That's how far I will ask in terms of non-positive curvature. Now, what about Morse quasi-geodesics? So, the definition is the one that you have seen, except that I've stated it for geodesics, but the same thing works for quasi-geodesics. I'm just asking that whenever I join 2 points by a quasi-geodesic, that one sort of fellow travels depending on the constants of the quasi-geodesic. So we can say that there are sort of directions of negative curvature. And in a hyperbolic space, so just to tell you that indeed we're talking of course negative curvature, in a hyperbolic space all quasi-geodesics are Morse. And in fact, it's an if and only if statement. It's an old theorem of Bonk. The other way around is true as well. So if we have a space and we know that all the quasi-geodesics are Morse, but obviously we have to ask for the same constants, for the same tubular neighborhood given the same constants, then this one is Gromov hyperbolic. So it is indeed a way of detecting Gromov hyperbolicity in my sort of larger space. Now, the bad news is that if you look at these objects in general, a lot of the things that were true in the rank rigidity are not true in general. So for instance, in the rank rigidity, one of the things that one could immediately deduce was that if we have rank 1, so that means we have a geodesic of rank 1, then we have a periodic geodesic of rank 1, and therefore an element that is Morse. This does not happen in general. There is an example of Elizabeth Fink. And another thing that may not happen if we have a Morse element, so again the rank 1 case, that does not necessarily imply that we have free subgroups, free non-abelian subgroups. So, I mean, if we just work in the very general setting, nothing of the things in the rank rigidity theorem are going to happen. So we will have to add some extra condition in order to avoid all these pathologies. And for instance, this kind of non-positive curvature condition will be one of them. Okay, so now commercial break. Why should we be interested in Morse elements and Morse quasi-geodesics? First of all, the existence of Morse quasi-geodesic is a quasi-isometric invariant feature, so it's an obvious way of investigating the geometry up to quasi-isometry. Then, when we work with groups and with random walks, in many cases of groups, we have examples of the kind random walks see mainly Morse elements. So as we move along with random walk, it tends to see only Morse elements. So we have kind of things like that in the setting of Mappley-Krauss groups and many others. Then they yield boundaries, and these boundaries are very interesting. I should begin by saying actually that in general the Morse boundary is not compact. We have compactness if and only if the group is hyperbolic. So in general it's not going to give something compact, but still it's really nice. And for instance, it can provide models of Poisson boundary for finitely supported random walks. And then I'm sure there are more recent results. They sort of appear naturally for actions. So for instance, if we have actions, if a group acts acylindrically, so our old result is about simplicial trees or hyperbolic graphs with uniform local finiteness, then we automatically have Morse elements because every loxodromic element in there is Morse. So that means that as soon as the action is non-trivial, we automatically get, for this kind of actions, we do get Morse elements. So now we go back to, we would like to retrieve a number of things that we had, for instance, in the rank rigidity result. So one way of understanding this would be, what would be the coarse version of dimension of the space of parallel Jacobi fields equal to 1? Because that was essentially, so in a way, in fact, in that case, we had that as soon as we have this sort of local property, it gives us a global behavior of the space, of the geodesic. So one could hope that if we grant this kind of phenomenon, maybe this is going to allow us to avoid all the pathologies. So this is formalized by the so-called Morse local to global property. I mean, there's a whole range of them. And in fact, in the end, I will focus on a very simple one. But let's say the general philosophy of the Morse local to global is we would like to work in a space in which if we know that the Morse property is satisfied up to a certain scale, then we know that we have it globally. So this would be, so sort of the quasi-local condition is going to give me a global behavior. And this is typically the case, for instance, for Gromov hyperbolic spaces. Well, in fact, in that case, what I'm about to say is that if I have a path, and if I know that it is a quasi-geodesic locally, then I know that it is a quasi-geodesic globally, because automatically all the quasi-geodesics there are Morse. It also happens for cat-zero spaces. So when we have honest non-positive curvature in the usual cat-zero sense, this phenomenon does occur. And it also happens for injective groups. These are some sort of groups modeled on L infinity in a certain sense. So I mean, I'm just mentioning it. Let's treat it as a black box if you didn't see the definition. But anyway, so this is a class of groups. And I think Urs is the expert in this, in here. Right, so this is, for instance, a kind of a kind of a property that we want to consider. And there is also sort of a weak version of that. So in this weak version, what we're asking two things. We're asking for the quasi-geodesicity to globalize. I'm not certain that the word quasi-geodesicity exists, but imagine that it exists. So this time what we're asking is that if we know that we have the Morse behavior up to a certain scale, we would be able to deduce that that path is quasi-geodesic, and we would be able to control the Morse property. I mean, to state the Morse property, but not for all the constants, only up to a certain constant. So it will only be true if the multiplicative constant is at most a certain big constant, and the additive constant as well. So not for all of them. Again, I mean, in truth, this is not going to appear here a lot. So let's look at this version. So, I mean, why would one, I mean, what can one deduce from these properties, like of globalization, and what would they bring? Well, to begin with, we can also look at this as a version of non-positive curvature, because obviously you've seen that this kind of phenomenon does happen when we have non-positive curvature. So it's yet another version of way of weakening non-positive curvature. Then it brings some nice information about the Morse boundary. So as I said, in general, it is not compact, but at least if we have this sort of local to global property, we can say that it is sigma compact, which is not true in general. So it's actually an if and only if statement, but only when we have the weak version already. And as I said, there are examples produced by Stefanie Zbinden of groups that do have a Morse boundary non-sigma compact. So we are indeed, I mean, it is a good thing that we can avoid this case, and we have sigma compactness of the Morse boundary. And then also, I mean, this sort of property allows for us to recognize if geodesic, or especially a periodic geodesic, is Morse or not, because that means I only have to check that it's Morse up to a certain scale, and then I can deduce that it is Morse. So for all this reason, it is a property that is useful, this Morse local to global. And now we'll move to the sort of the third, the other way, let's say, of measuring if we have negative curvature in our space or not. And this is the notion of divergence. And it's sort of actually very much connected, and in many ways, I mean, many kinds of behavior of the divergence have an equivalent expression in terms of asymptotic cones. So actually, in terms of the topology of asymptotic cones. So that means that now we sort of move to the study of divergence. And first of all, I will mention, how can one see some kinds of behaviors of divergence by looking at asymptotic cones. So the truth is, I did not know how much I should define of asymptotic cones. So the asymptotic cones are supposed to mean images of a given space seen from infinitely far away. So for the sake of completion, I will sort of go through the definition, like very briefly. Okay, so you need a device that is, so you need a sort of a generalized version. So the goal is this one. I'm given a certain metric space, and let's say I'm just, I would like to formalize an image of that space seen from infinitely far away. And in order, or actually before that, I would like to formalize something even more general. Let's assume that I have a sequence of metric spaces And I want to find a limit of that sequence. But a priori, there's no reason to believe that there is any sort of convergence. In general, there is none. So I have to find one. And for this reason, I need an extension of the notion of limit. And in order to do that, I need this device, the ultra filter on a set. So imagine that the set is countable, actually. So let's say it's n. And an ultra filter would be exactly this. So it's a finitely additive measure. So it's a sort of on the set of all the subsets of this countable set, and taking only values 0 and 1. So essentially, that means it just chooses a number of subsets of my given set. And an example is just the measure that tests if the set contains a certain point. And such a measure is called a principal or an atomic ultrafilter. And then we can define a limit of this. And the limit, given this omega, is going to be as follows. So I'm given a sequence in a topological space, and the omega limit of that sequence will be a point with the property that if I pick a neighborhood of that point and I look at all the elements in the sequence that are in it, this set of indices should be given the weight 1. So in other words, for this sort of strange probability measure, I would be able to say that the elements of the sequence are in this neighborhood omega almost surely. So here comes the magical thing. As soon as we have a sequence in a compact space, we have a limit, and that limit is unique. But there is one thing that's a little bit annoying. If we consider that particular case of ultrafilter, so the ultrafilter that tests if any subset in Y contains the point X, then that limit is just the element in my sequence that corresponds to the index X, which is ridiculous. That's not what we want. So we want a limit that would be a limit of a subsequence, so genuinely an accumulation point. So for that reason, we have to rule out exactly this case. And as it turns out, once we rule this case, actually we're in business. So we're going to work, therefore, with the so-called ultrafilters that are non-principal. So a priori, I'd simply rule out the previous case. So I'm saying I take all the omegas that cannot be written in that form. And this is equivalent to the fact that this sort of probability never gives weight 1 to a finite set. It always gives weight 1 to an infinite set. And once we do this, the limit that we obtain is the right kind of limit. So it's going to be a way of selecting for every sequence in a compact set the limit of a subsequence. And it's some sort of a clever diagonal process. So it's a clever version of a diagonal process. You can also see it as an application of the Hahn-Banach theorem. So you take the functional limit for sequences, for convergent sequences. You want to extend it to bounded sequences, and that's a way to do that. And once we do this, we can define a limit of sequences of metric spaces, as I said. So we take a sequence of metric spaces, and then we define the limit using this device omega, so therefore the ultra limit in the following way. We take products, and therefore we take sequences. And then the distance, well, I mean, the sequence of distances is going to be a sequence of values in this compact set, 0, infinity. But then obviously we don't want a metric space in which the value infinity would be possible for distances. And therefore we restrict. And we restrict in the following way. We consider for each of the sequences of points a so-called base point. So in X1, I consider E1, A2, and so on, En. And we only work with subsequences, with sequences that stay within bounded distance of my sequence of points. And once we do this, so this is going to be my space, so it's a subspace. We are going to have a distance that takes value, finite values. There's still the problem that we might have different sequences that give the distance 0, and therefore, obviously, we have to separate. So we consider the equivalence relation sequences at distance 0, and that is going to give us the ultra limit. So the image of that is I have the sequence of points, and I can assume that at each point, I'm just taking a picture of xn, and the center of my camera is en. And in the end, I have this device that will select a subsequence that converges in a certain way. So that is the ultra limit. But now we are interested in actually investigating only one metric space or only one group. And the way to do that is we just look at that metric space, and we consider a sequence of distances where we rescale the given distance by a certain scalar, and this scalar goes to infinity. And the limit, a limit that we get in this way is so-called asymptotic cone. So that means that in this sequence, in fact, now each time I have the same space. Obviously, we still have to have base points, and the difference is, what we're doing here, it's as if at the step n, we would observe this metric space from infinitely far away, sort of. So we would be at distance dn, and we would look at it from that distance, and would take a picture from there, and then we consider the sequence of things thus obtained, and we get the asymptotic cone. And there are a number of things that we can say with the topology of asymptotic cones about the natures of groups, for instance. So in the case of groups, obviously, the choice of the base point is irrelevant. We can always assume that it is the identity because it's homogeneous. And there are a few things that are very nice. Because they tell us that the topology of the asymptotic cones tells us a lot about the group. So for instance, asymptotic cones are proper if and only if the group is virtually nilpotent. So that means out of the virtually nilpotent class, these are like sort of highly not proper. Proper means the balls are compact. Then we can also recognize Gromov hyperbolicity. It's if and only if all the asymptotic cones are real trees. And there is a nice observation due to Kapovic and Kleiner. In the case where the group is already known to be finitely presented, it suffices to know that one asymptotic cone is a real tree, and we get that the group is hyperbolic. And then you can also recognize if a quasi-geodesic is Morse. So it is Morse if and only if in every asymptotic cone, its limit is composed of global cut points. So the picture is like this. If we are in a metric space, just any metric space, and we know that a certain quasi-geodesic is Morse, we can detect it in the asymptotic cones, because in every single asymptotic cone, it will be, so each of its points are going to be cut points. So in fact, the picture of the asymptotic cone in this case is going to be, it is composed of large chunks without global cut points. And this Morse geodesic is transversal to all of them. And in a way, the asymptotic cone is some sort of tree of pieces without global cut points, and Morse geodesic is transversal. Another way of detecting, and so again, a part of this equivalence is to say that the divergence along this geodesic is superlinear, which brings us to divergence. And as I said, this is actually very much connected with the topology of the asymptotic cone. So let me move on to the last sort of way of measuring non-positive curvature and negative curvature. So it's a notion of divergence. I'm going to use a version that we introduced with Charles Moses and Mark Sapir. So there are several ways of defining a divergence function. And, but they all sort of pretty much measure the same thing. So the idea is always the same. We are looking at, say, how to join 2 points. And so we pick a third, which is at distance of the 2 points sum d, and then we see how we could join the 2 points by avoiding a ball around this point whose radius is a fraction of that distance, so I don't know, some theta d. And we look at all the paths like this, and obviously we take a supremum, and this is going to be a way to define the divergence, and there are various versions of that. One of them is just the one that I described, so we just try to avoid any ball around any point. The second one is we restrict ourselves to points such that the distance, so let's say, I mean, in a way, actually, the points that are too close to A or to B are irrelevant, and the same happens with the points that are too far. And the third one is, in fact, we're actually restricting to points that are on a geodesic or on a quasi-geodesic. So in this case, what we're really looking at is a picture like this. So how can we join 2 points by avoiding a point on a geodesic? Let's say even the middle, because that's not very far. So for each of these definitions, we have a divergence function, which consists in I'm taking all the tripole of points such that the distance from A to B is at most 10. I'm measuring the worst, and that is going to give me the divergence. And let's say these functions are equivalent in a sort of an obvious case. So I mean, I wrote the case for, like, say, a metric space. But so in particular, all these notions are equivalent if we work with a finitely generated one-ended group. So obviously, if the group is not one-ended, that means it splits as an amalgamated product over a finite group, unless if it is virtually cyclic, that's not interesting. And if it splits, then essentially we'd better restrict to one-ended components if we can. So it sort of makes sense to look only at finitely generated groups that are one-ended for this kind of thing. And more generally, if we have a space that is one-ended, and in that case, what we need to ask, but we have it automatically for Cayley graphs, is that within the neighborhood of every point, we can find a actually quasi-geodesic bi-infinite. But in Cayley graphs, we always have that. So this is to say that it doesn't really matter. All these are variations. For one-ended groups, there's only one divergence function. And let me say what are the uses of this one. To begin with, it is a quasi-isometric invariant. And it was introduced by Gersten, but not exactly in this form. So he was looking, it was more defined in terms of rays. So we look at rays, and we essentially look at this picture, but the thing is A and B move along rays with origin C. So it was like explicitly a way of measuring how rays diverge. And at the time, he used that to distinguish various kinds of three-dimensional manifolds. And he proved that we only have 3 kinds of divergence: linear, quadratic, and exponential. Exponential comes with whenever there is at least a hyperbolic component. And quadratic, interestingly, so this comes, for instance, for graph manifolds. And it corresponds precisely to, so if we have graph manifolds and we glue them, it corresponds precisely to rank 1 geodesics, so to things that travel across the various components. And for such, so this one is going to be a periodic rank 1 geodesic, but the divergence along it is not going to be exponential, it's going to be quadratic. So this is to tell you that the sort of similarity, so let's say what I was saying, which was essentially rank 1 geodesics are almost like hyperbolic, this has some limitations. So for instance, I mean, in a hyperbolic space, the divergence is exponential, but in general non-positive curvature, the divergence can be anything. And in fact, so in the mapping class group, for instance, the divergence is quadratic. And Natasha Makura and myself and Jason Birstock actually proved that we have cat-0 groups, so groups of non-positive curvature, in which you have rank 1 periodic geodesics along which the divergence can be any polynomial, so of any degree. So it's an illustration of the fact that I mentioned. And again, we go back to the most pathological cases. The examples of Olshansky, Austin, and Sapir using, as usual, small cancellation. So they built amenable groups via certain techniques. So there are limit of hyperbolic groups, whence the definition of lacunary hyperbolic. So there are certain kinds of limit of hyperbolic groups. And these have superlinear divergence on some intervals. So when I say intervals, it's just the intervals in the domain of definition of the divergence. So the divergence is defined on R and takes values in, well, on R plus essentially, it takes values in R plus, and I'm talking about intervals in here. So on very long intervals, divergence can be bounded by linear, and on very long intervals, divergence can be superlinear. So one can have a lot of different behaviors for the divergence. And what is the connection between that and the topology of asymptotic cones, so images of the space from infinitely far away? We can detect linearity. So for instance, if the divergence is linear, that means that we have no cut points. So we have no global cut points. And let me tell you a few examples. So for instance, this observation allows one to detect a whole class of groups that have no cut points, and therefore the divergence is linear, because if we have cut points in one asymptotic cone, then the ultra power of G corresponding to the omega that we use for that asymptotic cone is going to contain free non-abelian subgroups. So in particular, if a group satisfies a law, then this cannot happen. In fact, we have an if and only if. So we can forbid the existence of a free subgroup in every ultra power by one and only one way, by asking that the group satisfies a law. So a law means an identity that is satisfied, so just a word that is satisfied when we input here any element, any set of n tuple of elements in my group. So a simple, for instance, a law is this one, and it's satisfied by abelian groups. Or this one, and it's satisfied by Burnside groups. So whenever we have a group with a law, we have no cut points. Now, another example that allows us to tell that the divergence is linear and therefore we have no cut points is if we have an infinite copy of Z in the center. Well, that's quite obvious, in fact. And higher rank lattices, in fact. Higher rank lattices are also without cut points. So this, for instance, corresponds to, let's say, the other case in the rank rigidity, because in that case, we had the case where the universal cover of M was a product of symmetric spaces, and the fundamental group, therefore, was a higher rank lattice. And that is the case where the divergence is linear and we do not have cut points. Right, so now coming back to what we can say about all this, in this very weak general setting of non-positive curvature, which is the existence of bicombings. So here is the first result. If we have a metric space with that kind of sort of weak non-positive curvature, meaning we have bicombing, the bicombing that I described, bounded and quasi-consistent, so that sort of way of associating to every 2 points a quasi-geodesic such that they sort of a small perturbation of the endpoints implies a small perturbation of the corresponding paths, then the the space satisfies the most local to global property. But in fact, that was just to use the terminology I introduced. It's much nicer than that. So within this condition of non-positive curvature, in order to check if a quasi-geodesic or a geodesic is rank 1, the only thing we need to check is the following thing. We have to look only at what happens at scale a certain d naught. And this scale depends only on the constants of the bicombing. So the bicombing, let me remind you, is a way of associating to a pair of points a quasi-geodesic. So this comes with with two constants. So it's going to depend on those. And then we have a way of controlling how they fellow travel by the endpoints. That gives another constant. This d naught depends on it. And the only thing we need to check is that when we join any 2 points on my quasi-geodesic gamma by a polygonal line of at most 12 edges, all these edges are going to have to be this special quasi-geodesic. This is going to be, let's say, thin along this geodesic, meaning that if I take the midpoint in here and a sort of a small ball around it, or a sort of, let's say, delta ball around it, this polygonal line will have to go through this ball. So it's some sort of thinness. I wish I could say that we have it only for triangles, but for the moment, yeah. So if we have this condition of thinness along this geodesic, again, just at a certain fixed scale, then we can deduce that that gamma is globally Morse with sort of universal constants. So this is, let's say, a coarse version of the condition that we had in the rank rigidity. So in the rank rigidity, what allowed us to say that we have a rank 1 geodesic and therefore Morse was to check that the space of parallel Jacobi fields is of dimension 1. Well, that's it. This is the coarse version of that. So if we have this at every single scale d naught, then gamma is globally Morse. And so in order to do this, we need that. We need the quasi-consistent bounded by combing. If we weaken that to, so sorry, maybe I should first tell about spaces in which the theorem applies. Non-positively curved spaces in the metric sense. Spaces quasi-isometric to median spaces, whatever that is. So, I mean, if you haven't seen the definition, imagine spaces quasi-isometric to cat0 cube complexes. It applies to those, because obviously these are not a priori cat0. Injective spaces of finite dimension, locally compact. Heligraphs of bounded valency. Actually, yeah, so I mean, it's just a list of things. If you came across them, then please know that this theorem applies. This way of defining rank 1 quasi-geodesic applies. Cubulable groups and the spherical Artin groups and Garside groups. So, okay, so it's a long list. And I don't have time to define anything unless if anyone really wishes it, but it's there to convince you that it really applies in many settings. So we do have the sort of globalization from local conditions for quasi-geodesics. If we weaken the condition and instead of bicombing, we're just asking for combing, in that case, what we can globalize is being a quasi-geodesic. So please note that here I'm not saying that this is going to be a quasi-geodesic in the beginning. I'm just saying this is going to be a quasi-geodesic at scale d naught, and also at scale d naught I'm going to have this phenomenon. And from that I'll deduce it is a global quasi-geodesic, and in fact it is Morse. If we weaken the assumption, instead of bounded by combing, just bounded combing, we're going to lose part of this. So we're going to be able to globalize being quasi-geodesic, but we're not going to be able to globalize Morse in general. We're going to be able to globalize Morse up to some constant, so it's the weak Morse. So we'll be able to say that a quasi-geodesic fellow travel, but with a bound on the possible constants. And yeah, I mean, the interesting bit in here is indeed the fact that the globalization of the property of quasi-geodesic. Then another thing is refers to the divergence function. So first there is a version in just terms of metric spaces, and then there is a version for groups. So for metric spaces, what we can say is the following thing. Under the same condition of weak non-positive curvature, so bounded quasi-consistent by combing, and also plus this sort of extra condition that we automatically have for Cayley graphs. So near any point we have a bi-infinite quasi-geodesic. We will be able to say the following thing. If we know that the divergence is bounded by a linear function on a sequence, then the divergence is linear. So that kind of phenomenon that I was explaining for the exotic examples of Olszewski, Osin, and Sapir is not going to happen here. So for these spaces with this sort of version of weak non-positive curvature, knowing the behavior of this divergence function on a sequence will be enough to show that it is linear altogether. This is a kind of phenomenon that is not very, does not appear very frequently. So, I mean, it's the kind of thing in which we're looking at a quasi-isometric invariant, and from a behavior on a divergent sequence, we'd like to deduce a global behavior. So, for instance, it is known for the growth function. So, for the growth function, under certain assumptions, if a group has a polynomial growth function on a subsequence, then the group has a polynomial function altogether, and the group is virtually nilpotent. And there are similar things for the Dent function. Well, actually, one example is the one that I mentioned. If we have a finitely presented group, and we know that the Dent function is linear on a sequence, then it is linear globally. And this is yet another instance of that. So the divergence becomes linear globally under assumption of non-positive curvature. And usually these kind of relations translate into the language of asymptotic cones in the following way. If one asymptotic cone is of a certain type, then all the asymptotic cones are of a certain type. So for instance, the theorem that I mentioned, the one of Kapovic and Kleiner, was exactly like that. If we have a finitely presented group, and if we know that one asymptotic cone is a real tree, then we know that all the asymptotic cones are real trees, and the group is hyperbolic. Well, we have something similar in this case, and let me maybe mention this result, and I will finish with that. So there is a version of it in the case of groups. And in fact, this last theorem is, let's say, the best that we can do in terms of eliminating all the pathologies and getting something that is not very far from what we had, in the rank rigidity theorem. So this time, we consider a metric space with the similar condition as before. We don't need to ask for this one because we have a group acting on it. But other than that, we're asking for that sort of weak version of non-positive curvature, which is we have a bicombing that is bounded and quasi-consistent. We also have to ask that it is G-equivariant. And we're asking that we have a group acting geometrically on such a space. So that means properly discontinuously and with bounded fundamental domain. It doesn't need to be compact. And then we have the following dichotomy. Either we have that all the asymptotic cones are without cut points, and therefore the divergence is linear, or we are in the other situation. All the asymptotic cones have cut points. Not only that, but the group has a Morse element. It is acylindrically hyperbolic, meaning that it acts in a certain way on a hyperbolic space, which guarantees that we actually have free non-abelian subgroups composed of Morse elements. And yeah, and obviously for all these reasons, all the asymptotic cones have cut points. So this in fact tells us that with this assumption of non-positive curvature, which is the existence of a bounded quasi-consistent bicombing, we retrieve some of the results that we had in the rank rigidity theorem. And I think I'll stop here.